So today we'll cover transient problems, all right? One of my favorite subjects is dynamics because most of the problems you encounter in real life, some of them are static and some of them are dynamic in nature. I do a lot of work where heat transfer, for example, can be a time-dependent problem. Just looking at steady state may not be the right answer, right? When the structure reaches equilibrium, that may not be the point at which the stresses are the largest. Maybe the stresses are largest earlier in time. Typically, in my experience, when you have high thermal gradients in the structure, you could start seeing problems in the structure, as an example. And so, for that reason, I think it's important for us to talk about dynamics in this course. So let's consider it, simple transient problem. Very simple. dy dt plus y minus 1 equals 0 with the initial condition. This initial condition is y at 0 equals 2. Now, everything you've seen in this class so far has been differential equations that are, or partial differential equations that are dependent on the spatial domain, not time domain. So be careful. This is not dy dx. This is dy dt, where t is a time, is time basically. Okay, and then now when I say y at 0, this is t equals 0. The initial condition, at the initial state, y has a value of 2. The exact solution to this problem can be found very easily. Okay, but one thing we could do, instead of using the exact solution, we can use a numerical method. Let's say we use a forward difference method. And some of you may or may not be familiar with this. I tried to construct a lecture today so it's independent upon your past experiences. Okay, so let's look at a forward difference method. In the forward difference method, what we're trying to do here, we're trying to approximate dy dt. And if you look at this, it's basically delta y divided by delta t. That's a good approximation to that, as long as delta t is small. Okay, key there is delta t is small. You see what I'm saying? And as the limit of delta t approaches 0, then I encounter basically the exact value of dy dt. So if we evaluate this derivative at a time, and let's call this a previous time. Anytime I say I minus 1, that's probably like a previous time. Okay. Then I can find that the approximation of dy dt is basically the slope, y at the current time minus y at the previous time, divided by the change in time, this time period, right? This time step from the previous to the current one. Okay, that interval is delta t. Okay, and so now I have an expression here that relates dy dt in an approximate manner as a function of what the value of y is currently, and what the value of y is previously at time, say, the previous time step. Okay. Now, if I go back to the differential equation, so now I go back to this differential equation right here, okay, and I look at that differential equation, but I look at it at the previous time step. This, I hope is true in the previous time step. I hope it is. So what I'm going to do, I'm going to substitute the value of dy dt I minus 1, previous time step, and I'm going to take that and plug it in there. Okay? And the idea is that when I do this and I plug it in there, now I have y at the current step, y in the previous step divided by delta t, plus y at the previous time step equals, or minus 1 equals 0. Okay? So this statement we can use to solve for the current value of y at this moment in time. And so if I solve it, so I bring this to the right-hand side, multiply by delta t, isolate y at the current value, what I find is an expression for the current value of y as a function of the previous value of y, and then there's a delta t in there. The cool thing about this is that if I know the initial conditions of the problem, if I know hey, at t equals 0, y is 2, then now I can substitute the value of y here, 2, and if delta t is small, say 0.01, now I can predict what the time is, what y is at t equals 0.1, the very next time step. Okay, I did that in spreadsheet format. So actually it took, I had the spreadsheet if you want it. It took me like a couple of minutes to construct it. This is, P is the previous value, N is a new value. I took the previous time is 0. At the beginning, y is 0. Sorry, y at time equals 0 is 2. That was the initial condition, if you remember. The delta time step I want to take to find out what y is in 0.1 seconds is basically 0.1. You know, I chose as 0.1. I could have done 0.01, you know. And the new time step, so the new time is basically the previous time plus the change in time, the delta t, and I get 0.1. So it's basically Tp plus dt equals the new time. And if I use this formula that I just constructed, I find the value of y at time equals 0.1. Okay? And I can now, recursively, now that I know the value at 0.1, I can substitute it back here, and I can march forward again. I can find, hey, what is the value at time equals 0.2? And if I do that, I can find the value of y at time equals 0.2. And I basically made this cell equal to here. So my previous is that one is connected to that. So in Excel, I just dragged it down. And in essence, what I have here is a value of y, the value of y as a function of time. Okay? And when I compare that to the exact solution, I'm within 1% error. Okay? This here, what we see here is the forward difference method. Okay? Any questions on this simple methodology, which we just constructed in very few steps? No questions on that? Okay, excellent. So let me cover the next one. The next one is backward difference. Okay, backward difference. When I look at backward difference, now what I want to do is use the same differential equation, but pretend that this is true at the current time step. Okay. In the previous methodology, the forward difference, I was presuming that this is true at the previous time step. Now I'm looking at the differential equation as this being true at the current time step. So if I now look at dy dt I, and I approximate that, I find that dy dt is I minus 1, yi minus y, I minus 1 delta t. Okay? In a very similar, very similar fashion, I can plug this in here for that, and when I do that, I can now solve for yi, okay, the value of yi. What you notice here is I had to take divide by 1 plus delta t, which I did not have to do previously. You know, so it's a slight difference between the two methods. One gave me an expression that looked like that one, but the current expression I got looks like this one. Okay, slight difference. But when I look at what I get, okay, and if you're looking for the difference, the main difference here between this equation and the previous one, that instead of yi minus 1, I have yi. That's the only difference. And yet the equation looks different. However, when I look at what this produces, and I follow the same process, so I start at time equals 0 with an initial condition of 2, so y at t equals 0 is 2. And I march forward in time, so dt is 0.1. By putting these two values in here, I can find y at the current value, time equals 0.1. And when I do that, I got 1.909, okay? And then I can use that as a previous time and then keep marching forward. Okay, it's a recursive formula. You know, once you have yi minus 1, you get yi. Next time, the old value becomes the one that you put here, and then you get a new one, and you just keep marching forward. Okay, and when I do that, the error is again within 1%. You know, pretty good, pretty good actually. All right, so that's we're looking at a method called finite difference, okay? And we're discretizing the time domain using that methodology, okay? There's a question here.
Yeah. So it looks like your error is increasing with each step. Is that going to go unbounded?
So excellent question. I'll cover that in a couple of minutes. But what is important, what was the fundamental assumption we made here? What is the main assumption we made? The main assumption we made was that dy dt, right, can be approximated like that. And this is going to be very close to that as long as delta t is small. So in essence, we want to keep delta t small to be able to have less error. But the problem is if it's delta t is too small, your analysis may take months to run, right? So you have to kind of find a balance, right? So it depends on the problem. And you have to be you have to look at the problem you're working on. Maybe the problem you're working on, the loads that are applied to the structure are slow over time. Or if it's slow over time, maybe the structure won't have time to respond. In those scenarios, you can look at larger time steps because things are not changing very quick, right? If we think about it, I was working on a project where things were happening in hours, right? So here, 0.1 looks small, right? But in another application, 1 hour could be small. Right? It depends on the problem. Okay? In the one problem I was working on, everything was happening in hours. Okay? So I had to find out, a good balance. Me running a model at every 0.1 seconds doesn't make any sense. Nothing is changing. Everything is changing in hours, not 0.1 seconds. Likewise, you can have problems where things are happening in a fraction of a second, like an impact dynamic event or a hail impacting a composite. And I want to know how the composite structure responds, which is a good application for aircraft structures, right? In that application, I want to know if the hail damage, what kind of damage is going to do to the composite. There, I probably want to reduce the time step to scales that are even less than 0.1 seconds because everything's happening maybe in microseconds, right? There's another method called a central difference method. In this case, we're evaluating y, but now we're evaluating this differential equation, and this differential equation is true between the previous time step and the current one. So it's somewhere in between. So this is a true statement somewhere in between. And in here, the main difference, this equation is the same, so I'm going to use that. I'm not going to change anything there. But y here is basically the average between the value before the previous one and the current one. So the average between the two. That's the main difference between the previous method that we just discussed. And when I take this in and plug it in here, and I plug it in the approximation for dy dt in there, I want to solve for yi. That's what I did. You can go home and try it out. It's going to work out very nicely. When you do, you get the value of yi. It looks complicated, fine, but it's just the value of yi. Okay, it's just algebra. And when you work through this, and now I use Excel, and I can provide you the spreadsheet if you want to see how I did it. Very simple. We again have an initial value of t of 0, and y is 2 at time equals 0. And I can now, again, march forward in time, because if I know yp at time equals 0, then I can substitute it here, so that's 0. And the delta t now, because I want to march forward, is 0.1, say. So 0.1, 0.1, 0.1. Now I can find a new value of y at time equals 0.1. And then once I know the value of time at time equals 0.1, I can take the value of y, plug it back in here, and march forward again. I can change it from delta t to 0.1. I can go to 0.2, say. I can change the time steps, right? And then I get the new value of y, and then so forth. Just keep moving forward. And when I check that, again, now look at the error. The error for the same time step that I took, 0.1, 0.1, everything is 0.1 time step, marching forward. I find the error is actually like 0.2%. It's very small. compared to the backward difference and the forward difference. The forward difference was 1%, backward difference was minus 1%, and here I don't even know how to calculate the percentage errors, it's so small, okay? And so now that we see this, let's talk about a few things here. So all three numerical solutions, central, backward, forward difference, yielded very, very similar results to the exact solution. So did I have to look at a book and find out what the solution to the time domain differential equation was? Or no, I could very simply in Excel, I was able to implement a solution procedure that gave me the value y as a function of time. Okay, that's wonderful. The central difference outperformed the other two methods. A smaller time step does, and you can try it at home if you want a spreadsheet. I can email it to you. Will yield even more accurate results than what I've shown here. But smaller time steps means more computational time. Okay, that's not something desirable in all cases. I want you to note that in the central difference and backward difference, we had to do some division calculation. We had to do some inversions. I want you to see that here when I look at the formula. Here I had to divide by 2 plus delta t. Here I had to divide for 1 plus delta t. That's backward difference. And then in the forward difference, I didn't have to do that. Okay? This will become important later when I discuss computational expense. Now, the one thing I want to point out, the forward difference method can become unstable. If I use large increments, large steps in my marching procedure, it will diverge from the exact solution. And in some cases, it will start oscillating in a way that's not physical. Okay? The forward difference does that. The backward difference tends to be stable, independent of the time step. But that doesn't guarantee the solution will be accurate. It's not going to grow. The error is not going to grow unbounded like it does with the forward difference. So we will try to discretize the time domain using finite difference and discretize the spatial domain using finite elements. That's the way we're going to do it. And going back to the previous point I wanted to make is that I'll cover this more a little bit later on, just in a couple more charts. But the forward difference method is cheap. I didn't have to divide by anything. And you will see that in a few examples how simple it is to implement. Now, how we tackle transient problems. I already taught you finite elements. With finite elements, we discretize the spatial domain using finite elements. That's what we used. But what we're going to do is the time domain aspect of the problem will be discretized differently. It's going to be discretized using finite difference. So in essence, we're going to separate the variables, and that will allow us to actually model the time-dependent behavior of many different problems. Heat transfer, elastic bar, or impact problem. I can drop say I have a cantilever beam, and I drop a mass, and it hits the cantilever beam. Well, that maybe the structure will start vibrating, right? We can do these kind of things in Abacus or any commercial code. You can actually write it yourself. In fact, when I teach you this, I hope you can, because I'm teaching you the theory. And also, you'll have your homework. Absolutely. So if you're not very familiar with coding or don't feel comfortable working with MATLAB or Fortran or C++, then I do suggest you start looking into that, starting to get familiar with that, because you may need it for some of this. Doing it by hand is not always practical. At some point, doing it by hand can take you so far, right? At some point, it can become a little bit too painful. All right, so let's look at the approach for transient problems a little bit more, but now in the context of a real problem. Let's consider this transient problem. Here, I didn't put any physics into this transient problem. There's no real physics here. It's just an equation, and it's a partial differential equation. You have partial differential. You have derivative w, double derivative w, respect to x. X is a spatial domain, so maybe I have a 1D domain in this case. And I have derivative of W respect to T. This is a time domain type of derivative, okay? So in this particular problem, I'm going to say that for any point in time, at any point in time, okay, at any point in time, at X equals 1, W, we're going to make it 1, okay? We're going to make the value of W 1, okay, at X equals 1, so that this domain goes from 0 to 1. We'll make it 1, we'll make it 1 at this end at any point in time. Okay, that's what that's saying. The second boundary condition here says W prime at X equals 0, comma T equals minus 3. Well, what this is saying is that at any point in time, the value of this domain, W prime is minus 3. So the slope of W is basically minus 3. Bottom line. The third boundary condition that this problem is giving us is that W, and by the way, W is not deflection. We don't know what it is. It's just a transient problem I'm giving you here. Okay. What differentiates this problem from the previous example I gave you, there's no spatial domain over there in the example I gave you previously. It was just time domain. This example has time domain and spatial domain, which is more applicable to what we're really looking for here. Okay. The value of W, now check this out. W at any location between 0 and 1, okay, the initial value of W, because T is 0 here, the initial value of W is 1. That's what that's saying. Okay? And you may say, why I'm spending so much time in these boundary conditions? You know, because sometimes you can work the problem mechanically and not understand what's going on. And I'm trying to bring a little bit of, it's not even physical problem, but I'm trying to bring it some meaning to you so that when we're going through this, you're not getting lost. Okay? The second thing I want to point out is that now that I have this strong form, isn't this a strong form here? It's true at every point in the domain. Okay, at every point in the domain. What I'm going to do, I'm going to formulate the weak form. And one of the feedbacks I got from talking to Leonardo is that many of you are confusing the weak form Galerkin to developing the weak form. Doing what I'm doing now is not the weak form Galerkin. What we're doing right now, we're developing the weak form. Okay? This is not called the weak form Galerkin by any means. Okay? So I want to make that very clear to all of you so when you're working this through, you're not confusing the two. This right now is a weak form. And what we're going to do is multiply this residual function. Everything is on the left-hand side is equal to 0. I'll call this residual function. And I'm going to make that orthogonal to weight functions v. So what I did, I took that partial differential equation, multiplied it by v, and integrated this over the domain. This right here is a weighted residual. And notice now that there's time domain in there and there's x in there. So we're not talking about just a time domain problem. We're not talking about a spatial problem alone. Now we're talking about spatial and time at the same time. Okay? Make that very clear in your mind. Okay? In the previous example, everything was just a function of time. But in this problem, W can vary spatially between 0 and 1, x equals 0 and 1, and between those two bounds, W can vary as a function of time. And I decide when I stop. Right? Isn't that true? I can continue finding what the value of W is tomorrow. Up to tomorrow. I can run the analysis and find out, okay, in 200 days, does the value of W change? I can do that. Right? There's some applications that you may want to know. You may want to know what the value of temperature in a particular application is over several days. Maybe it's oscillating because the sun is hitting it, and then in nighttime it's cold, and then maybe in the daytime it's heating up again. And I want to find how time is changing over maybe over the floor of this building, right? So there are many applications where you may have to do that. Okay. And so the next step is that this is still the strong form, but in the weighted residual format. And we've already learned that in this format, we still want to be able to reduce the continuity requirements so that we only have to satisfy the essential boundary conditions of the problem. And to do that, and now I'm no longer, from now on, I'm no longer showing you how to integrate by parts. Everybody here should be able to do it by memory, almost. Like, you can look at this and put v on the left, put this on the right, take one derivative off, put the other one on the v, and then do plus, minus. I'm not going to do that again. From now on, we're done with that. I already showed you how to do that. You know how to share the derivative with v. And all you're doing is sharing that with v. Because there's two of them there, split it in half. Keep one there, put one there. But you guys already know the process. And so here, that's a time derivative. With a time derivative, you're not going to touch that. Okay? Even if it's second order, I don't know. If it's fourth order, I don't know. I think there is a situation where you can be like fourth time derivatives. I don't know. You're not going to touch that. Because this one we're going to deal with differently. That one we're going to deal using finite difference. Okay? And I'll show you later. Don't worry about that. But now let's integrate parts. And when you do that, this goes back into the integral. And almost by memory, you can imagine the plus, minus, and the minus one goes inside the integral again. And then you have your boundary terms, which are on the right-hand side given here. And the thing I want to draw your attention now is I don't want you to forget that W is a function of time. But now W here is evaluated at one end of the boundary. And here W is also evaluated at one end of the boundary, the other end. There's at one end, and there's the other end. Now, notice how W could vary as a function of time. At one boundary, W can vary there. It's very likely. It could happen, right? So keep that in mind when we work this through. One small error or significant error that needs to be corrected is that this weight function that we're selecting here is not a function of time. That's an error of my part. So we're making the error orthogonal to v, and v is only a function of the spatial coordinate. Okay. All right. So now we got this down, I could now approximate a solution using weak form Galerkin. That will be my next step. How do I use weak form Galerkin now? And that's not a very difficult thing to do because we already learned it. I will use a linear element just to keep this example simple. Okay. I'm not going to do isoparametric here because then I'm adding too many different concepts combined, and I think it will be overwhelming. And I think you got to learn things little by little. Okay. So, but I could have done that, and you know how to do that because the homework was due today, wasn't it? Okay. And so, so let's take the approximation function, and let me take the approximation function, which is a function of time and x, spatial domain, and I'll say, okay, remember before I just had wi nix plus wj njx with no time in there? What we're going to do now is I'm going to just say that wi and wj could vary as a function of time. So these nodal values here, they're unknown, could change over time. That's what we're saying. Okay. Let's that happen. We need to make that happen because that's how a dynamic problem works, right? Things have to vary as a function of time. And when I look at the shape function here, which you know what it is for a linear element, that is for the linear element. We realize here that the shape function is not a function of time, and I hope it's not, because I don't want my basis function to be changed as a function of time. We want to maintain that to be a function of just a spatial coordinate, because again, we're just discretizing the spatial domain. We're using finite elements. We're not discretizing the time domain using finite elements. Okay. And you wonder, well, these shape functions are the same as what I got before? Yeah, absolutely. Let's see if it's true. If at x equals xj, I'm at this end. Okay, so if I put xj, what do I get? This is 0. I put xj here. Xj minus xi is the length of this. So I get LE over LE, that's 1. So therefore, WXT, which is a function of time, at this boundary is WJ as a function of time. So it is true. Okay, I am getting that. Okay, if I plug in x equals xi, same thing. I plug it in here. This goes away. Xj minus xi is Le, right? So now I just get 1 here. So W as a function of time at x equals xi is WIT. Well, that is true. That's what we discussed. Okay. So now my nodal quantities that we were talking about before, which used to be not a function of time, are now a function of time. Okay. Hey, let's not change the rules of engagement. We'll just call this, hey, these are my shape functions. I'll put them in a vector n, matrix bold, so you remember. And this is just a function of x. Just remember that. And I'll lump in here Wi and Wj. I'll put them in D, in the vector D. And that will be a function of time. So D is a function of time, n is not a function of time. That's where the separation of variables is occurring right there, right in that step. We just taken Wx as a function of time and broken it into 2 parts. One that tracks time at the nodal values, and n is your shape functions, which are not a function of time. They're just function of x. Okay, is that clear? And I realize these concepts can become quite complex, but I do think that if you have questions, just go ahead and ask. Don't be shy. Okay, so now I think the next step is quite simple. Actually, we just take this approximation function and plug it into my weak form to enable weak form Galerkin. Now we're talking about weak form Galerkin, and what I'll do is just plug this into my approximation function and select V as what? What do I select my weight function to be? My basis functions, which are what? My shape functions. They're the shape functions in this problem. And again, I do have an error here. V, which is my weight function, is not a function of time. It's just a function of x for that domain. Okay, so now that I got that right, one of the things I like doing personally is I know I have to evaluate W as a function of x, V as a function of x, and W as a function of time. Why we don't do that now, so we prepare to deal with it. And so since I have W, which is this here, I will go ahead and do that. Okay, so Wx, which is a function of time, that's that equation there. I'll take the derivative of W respect to x. Okay, when I do that, I realize very quickly here that W is not a function of x. This Wi, which is a nodal value, is not a function of x, and Wj is not a function of x. What is a function of x is the shape functions, and so for that reason, when I take the derivative, I just focus on the n's. That's what I'm doing there. And when I take that derivative, you find that I get minus 1 over Le and minus 1 over Le. Okay? And now, once again, I can put minus 1 over Le in that vector. I'll call it B bold. And Wit and Wjt, which are basically the same vector D. I haven't changed that portion. Everybody follow so far? Excellent. Excellent. All right. So now, I also know from looking at this that I have to evaluate W as a function of time. And, I do think you should spend some time at home going through it, re-deriving it, because it can be confusing. But did we talk about shape functions not being a function of time? Yeah, we just said that. And so therefore, when I take this derivative, I have to take derivatives with respect to Wi because that is a function of time. That indeed is a function of time. I have to take that derivative. Same here, okay? And so if I call this Wj dot, just to simplify the notation, and I do agree with some of you, it is scary when you see like a W dot on top, because it's kind of like a symbol. But just keep in mind that's just a rate of change of that variable. Don't lose track of physics, okay? So I'll put this in a vector again, but now that vector, isn't this the same as D, but derivative of D as a function of time? So I'll just call that D dot, and D dot contains these 2 quantities in a vector, column vector. While Ni and Nj, do you think that changed when I took this derivative? No, it didn't change. That definition is the same one I had at the beginning, which is N bold. So in reality, derivative of W with respect to t is essentially N bold d dot. Okay? Any questions in what I just did there? Very critical point at this time that we've reached. Okay? Any questions? Okay. I'll select V. I'm going to select V here. And again, another area is not a function of time. I'll select V to be the basis functions. Okay. And so if I do that, I get for W, derivative of X, that was basically B bold times D. I select for V, I selected the N bold, right? Transpose. So the derivative of that gives me B transpose, bold. I also notice here that this quantity here, I just evaluated that just a minute ago. I call this derivative of W with respect to T. We found out as N bold D dot, in essence. While V was selected as N transpose bold. Remember, V we're selecting to be N transpose bold. Okay? And we also found the derivative of N transpose bold is basically B transpose bold. So that's what that turned into. Okay? And now on the right hand side, for each of the shape functions, for the weight function, I'm selecting each of the shape functions. And when I evaluate that, you'll find that the Kronecker delta property simplifies this to minus W prime at xi comma t and W prime xj comma t. So the slope potentially is a function of time at two ends, and that is your forcing function on the right hand side. Any questions on that? I love dynamic problems because it's kind of cool to see things change, right? All right. So hey, when you integrate this, it doesn't take very long. We know B bold, right? B bold, to remind you just very quickly, B bold was 1 minus 1 over LE, 1 over LE, but B transpose is in a column format. And then B transpose is minus 1 over L, minus 1 over LE, 1 over LE. Multiply those two, integrate that over the domain, and when you do that, you get this matrix right here, okay? And the D right there, bold, is basically WI and WJ for node I and for node J. And now when I also have to take this integral, which has a D dot there. This N and transpose N are known. We know those. So you can integrate that very quickly from xi to xj. I did it in Mathematica, decided not to show it here. When you do that, you get LE over 6, 2, 1, 1, 2, and that D bold, not to forget, is the rate of change of WI and the rate of change of WJ. Okay? And I just put that in there. So this is my element formulation for any element in the system. Okay? That is the element formulation. Any questions that you may have at this point in time? Anything that is not clear? Is everything clear? That is the element formulation. Okay. If I left it at that, it'll be too boring, so I think we should kind of see what happens next, okay? It'll be great to solve this problem and see what happens. Hey, let's do it. The problem was about, I told you in the initial problem, let me remind you, this is the transient problem, and I want to use 3 elements in this domain. That was, I forgot to state it here, but the idea was to use 3 elements to discretize this domain. Okay, equal elements, linear elements. Okay. So when I go back, I have my 3 elements. The length from one end to another at x equals 0 is here, and then x equals 1 is there. And therefore, since it's 3 equal elements, then each L is 1 over 3. Okay, element 1, 2, and 3. The values of the nodes are W1, 2, 3, and 4. Okay, and what I've done, since the element formulation is the same for everybody, I just number them. So for element 1, I have 1 and 2. Okay. I also notice very quickly that this is minus W1 prime at time t. So just to make that point, You see here I have minus W prime xi at t, right? So if I'm looking at element 1, say, right, isn't this W prime at node 1, in essence? That's what it is. That's why you see that there. And then for second element, I have the same thing, but the connectivity is 2, 3. So I have 2, 3, 2, 3, 2, 3. And then for element 3, I have 3, 4, 3, 4, and 3, 4. And the only difference now, I've substituted the value of L in each of these equations. They're equal. In this case, they're all equal. In some cases, we don't have to make them equal. Again, I just substitute the value of L, which is 1/3. So 1/3 divided by 6 isn't that like 1 over 18? 1 over 18 there. And then 1/3 gives me 3 there. So that's why you see those values that look strange. 1 over 18 and 3 there. Okay. Any questions on this part so far? Okay, excellent. So, hey, the assembly is the same process. The assembly process is using the connectivity. It's no different. You have to assemble this matrix here, which you have not dealt with before, and we have to assemble that guy right there. Oh, and the forces on the right-hand side. When I do that and assemble it, this is how it looks. I have a 4x4, 4x4, and I realize here that these middle terms cancel out when I do the assembly. And my goal now is to, now that I have the assembly of the full system, my goal now is to impose the boundary conditions. Those are the steps, right? Develop the element formulation, approximate the behavior over an element, right? Then discretize the domain, right? Assemble the system together, and then impose the boundary conditions. That's the step we are in at this moment in time. Okay. So we will determine the boundary conditions now in terms of the global unknowns. So what is important now at this step is you know the boundary conditions of the problem. Okay? And so we need to relate that to the problem that we have at hand. And if you remember, we said that W at x equals 1 t at any point in time is 1. And we said that W prime at x equals 0 at any point in time is minus 3. Well, that relates to the following. So x equals 1 is at the right-hand side, at this boundary. So that's W4. And what we're saying really is that W4 at any point in time is 1. We're saying that W prime at any point in time, at x equals 0, okay, at x equals 0 is, basically, at x equals 0, what was my node number? 1. So W1 prime at any time is minus 3. That's what we're saying there. And also, the one thing I want you to notice that's of importance is that I may not have given you the rate of change of W, but if I'm telling you that W at any point in time is 1, what is the rate of change of W over time? 0. Okay? I didn't have to give you that. That's obvious. Okay? And so that's important for you to know, because in many different applications, you may not, nobody gives you a problem in a silver platter and tells you, hey, these are the boundary conditions you have to give abacus. Or these are the boundary conditions I need to impose. You have to understand the problem, and this is one of the most critical parts in a dynamic problem, is to define the boundary conditions. Many of the problems I see when it comes to dynamic problems, no pun intended, problems meaning like issues with the problem that don't make any sense, have to do with the initial boundary conditions. That's usually the problems where I see them. They're usually, the initial boundary conditions don't make sense. One time I was working on a problem, and it had to do with a nozzle vibration because of the, forcing functions of basically the core of the rocket was blowing significant amount of acoustic vibrations into the engine. Well, what initial boundary conditions you put in there, right? So initially I ran it, and nothing makes sense. Everything was dramatically going crazy. And so when I realized that my initial conditions, which is the thing is that when you, and the guys here in the back work in industry, they work in a lot of different problems, more than I do probably. And they can tell you more than I do. It's exciting to kind of mesh it and apply the loads. You run it, and because the mesh looks so cool. I mean, you do the whole thing, and you feel, man, I'm getting close to done. Because you see that mesh, and it makes you lose touch. I'm just telling you from my experience. And you realize, no, hold on, I'm not done yet, okay? I have a lot more to do. The mesh may look great, just ignore that fact. Trust me. Just trust me, focus on the boundary conditions, make sure those make sense, okay? And now that I feel like I have a good handle of these boundary conditions, I can now impose them. I have W1 prime t is minus 3, so that becomes 3, right? So that's 0, 0. And then W1 at 4, node 4, is W4 is equal to 1 here, and that's 0 there. So I have to impose those boundary conditions in this problem. And that's what I did here in the top picture as shown. I've applied the boundary conditions, and I realized here that I can just use the first 3 equations, really, to solve this problem. Okay? The only trick right here is the following. You will notice here that this is not 0. I have to be careful. So when I multiply this third equation by this column, I realize that I have 0 times W1 minus 1 times W2, 2 times W3 minus 1 times 1. Okay? Sorry, 3. 3 times minus 1 times 1. That's minus 3. I have to do something with that. So you can bring it to the other side of the equation. So since this is 0, you get 3 there. And that's why you see a 3 there. Okay, so I have 3, 0, 3 right there. And everything is reduced very nicely now. Let me call this C bold C. This matrix bold C. And I'll call this K bold K. Okay, so now what I really have is a system of equations. That's what it looks like. And I have C, which I know is not a function of time. Do you agree? C is not a function of time? I know those values. It's a 3 by 3. Do you agree that K is not a function of time? It's a 3 by 3. Do you agree that my force vector here, or I call it force vector, we don't know what it is. It's a problem that I just came up with. But this is not a function of time. So what is the only thing that's a function of time? D. That's what I'm interested in. I'm interested in how W changes over time. That's my goal. And if I know how W changes over time, I also know how the rate of change of W is over time also. Okay. At this point, we simplify the problem to a problem that can be tackled using finite difference. Okay. So I've used finite elements to discretize the spatial domain, and now nothing is a function of x. Everything is a function of time. Okay. Excellent. Excellent. Any questions you may have at this point? Are you understanding what we're doing here? Okay, I'll let you observe that because it looks new. But before, so that you see that this is not all that new, we didn't have this term. Now we have that term. Okay? If you're freaking out, many people freak out when they see that dot there. Nothing to be worried about. That's just a function of time. Okay? That quantity is a function of time. That's all we're saying here. Now I have another differential equation. I thought I was done. Remember, so when we didn't have the time domain, and I did the spatial discretization, I went from the differential equation, or partial differential equation, down to KD equals F. And I was done. Just invert that, I'm done. But now I went through finite elements, discretize the spatial domain, and I'm still stuck with a differential equation. The only difference is this is a function of time now, okay? Not a function of space, okay? So let's see how we deal with that. Hey, let's just apply the easiest one. We can just derive the backward difference formula. Let's just do that, okay? So let's pretend that this is true at the current time. What I'm saying is that this is true at the current time. That's what I'm saying. So di dot can be, do you agree I can approximate it using the slope between the previous time and the current time? And so therefore di minus 1 is approximate to di dot, and it approaches di dot almost exactly, or is exactly to that when delta t approaches as the limit goes to 0. That's the basic definition derivative. What I'll do now is plug in this form, and remember, these are vectors. These are vectors right here. Vectors of how many, don't lose track, so how many quantities we have in this vector right now? 3, don't forget that. So I plug this in here, right there, I plugged it in, and I want to walk through that. I'm left with that, okay? I'm left with that. My goal is, if I know the previous values of D, that I can determine what DI is. That's really what I want to do. But then I have to factor out DI to be able to do that. So I have to factor DI, and so I did that here, and that's equal to the right-hand side, which the rest of it. Basically, I brought everything else to the right-hand side. Okay. Now, this looks complicated, but it's just algebra. It's just algebra. I just had to work through a math to get it done. I don't think you should be worried. You know, this FI is that one right there. This DI was factored out. That's why you see 1 over TI, C plus K. And then you have this C times minus DI minus 1 delta TI. I brought that out of the equation. And so that's what I got. So nothing to be worried about. But just notice how, with a backward difference method, I had to invert this matrix right here. So I have to invert that, and then I can get the value of DI. So I invert that, multiply by this. And now, here, just to show you that we're basically done, is that we know C, right? We know K. It's a 3 by 3. That's a 3 by 3, 3 by 3. C is a 3 by 3. Fi is a 3 by 1. It's a force vector or whatever that was, 303 if you remember. These are all numbers, all numbers. The only thing that's not a number is delta Ti, the time step, which you can select, and this vector here, Di minus 1, which we can assume initially that we can give it an initial value. So we can start marching the solution forward. Okay?
Professor?
Yes?
Use a backward method for D dot. And can you, what if we use a forward method or midpoint method?
Yeah. So just like I showed, I don't want to confuse anybody here, but just like what we showed earlier, we did it with 3 different methods.
Yeah.
Forward, backward, central difference. The method is very similar. Okay.
Why do we have a 3 then?
Sorry?
What's the advantage?
Yeah, I'll cover that. I'll cover the differences with that. Okay, so, well, a problem is never complete if you don't complete it. So let's do a little bit more work so you can see how it works. So I have that. That's what we started with. We'll use this recurrence formula right here. And I know what C is. C is just this right here. So I plugged it in. K is right here. I plugged it in. C is right there. I plugged it in. And I have Fi, which I plugged it in. So now I'm really ready to go forward and start finding out what D is as a function of time. Of course, I'll start at time equals 0. That's sort of arbitrary when you start, right? So I can say T is 0 now and then figure out what happens next. Let's say, so I'm not done yet, okay? I'm not done yet. The one thing I want to point out, let's look at the original problem. The original problem as we spoke about. We say that W, okay, this is very important, guys. I'm not done with the initial conditions, by the way. W at any point, isn't this what we're saying here? At any point? Huh? That's what we're saying. At any point, but at time equals 0 is 1. So what we're saying is that the value of W is 1 at time equals 0, doesn't matter where I'm in between, right? So I provided an initial condition here. Then it still needs to be included, which I have not included. And what that is saying is that, hey, at W1, at W2, at W3, at W4, the value of W is 1 at time equals 0, okay? And so if I now substitute that as my first values of D. So at time equals 0, W1, so W, I forget now what the matrix looked like. Was it W1, W2, W3, or W2, W3, W4? Anybody remembers? Since I don't remember, many of you don't remember, so let's look at it. 1, 2, and 3. Okay, 1, 2, and 3. So, so 1, 2, and 3, we make it 1, right, for the D's. And I'm basically done. I just multiply everything out, and I get the new value of D1. Okay? When I get the new value of D1 at time, and that's at time equals 0.01, right? Because I'm marching forward with a delta T of 0.01 here. So since it's 0, and I have a value of 1, 1, 1, then at 0.01, I have a value of whatever I get when I multiply all of that. Once I'm done multiplying all of that, I'll plug it in here now. Okay? And then at time equals 0.02, with a time step of 0.01, I'll get the new value of W's. So now I know the value of W at 0.02, time equals 0.02. If I wanted to kind of cheat a little bit and go a little faster, okay, I can make delta T 0.03, say. Delta T 0.03, and then I'll be calculating the value at T equals 0.04 instead, because I started with 0.01. 0.01, and if I use a delta T of 0.03, then I'm at 0.04. So whatever I get out of here, I get it. That's the value of W at 0.04. Any questions on this? Any questions on this is a question here.
Is there a way to analytically determine what the time step should be before you...
Absolutely. Great question. I'll be covering that in a couple of minutes. This lecture is taking a little bit long, but we'll get there. Okay? Question?
So we have no limitation to change the time steps anywhere in the problem?
As long as the time step is sufficiently small for the problem of interest, you should not have a problem.
So we can start with this smaller time step there?
You know, one of the things I do, to answer your question, one of the things I do, I sometimes do trial and error, okay, to find out what's going on. And also, you know, many of these problems, you know the physics. You know the physics of the problem. And usually the physics of the problem dictates what is the time scale you're looking at, okay? And so you'll be able to figure it out, okay? But that's an excellent question that has a lot of angles we can tackle, you know, which will take me long right now to do, because this is just a random example. But we can tackle it with a real problem maybe later on, okay? All right, so, but the bottom line is look at the physics of the problem. The physics of the problem dictate, you know, how, you know, what kind of time stepping we need, okay? But there's another thing that we're going to be talking about in a couple of minutes. Okay. Okay, any questions? Okay. All right, so, I don't want to scare you a little bit, but that formula right here is a recurrence formula that's general for this problem. It's called the theta method. So you put theta there, and then theta there, and theta there. So just imagine if I have to keep rederiving. If I have to keep rederiving the forward difference method, the backward difference method, the central difference method. Well, what if I have a simple formula, okay, that can give me all three automatically? Okay, by just changing value of theta. So if I make theta equals 1, do you agree that this looks exactly what we had for a backward difference? Okay, some of you don't see it, so I'll show you. This is what we had for backward difference, this formula right here. Okay. Actually, stare at this formula. Sorry, stare at this formula. That's a better formula to stare at. Okay, stare at that. Okay. If I now look at theta equals 1 here, plug it in, that goes away, that goes away. I have Fi. Plus that equals that with theta equals 1. You see that? So that's the exact same thing we do right. Excellent. So that's awesome, because with that formula I was able to get backward difference. What if I now plug in theta equals 0? If I plug in theta equals 0, this goes away. This stays, that goes away. And now you can notice very quickly how we get this formula here for forward difference. You can actually derive it yourself if you want. Okay, it's very nice. And now I want you to notice as well that I had to invert the C matrix right there, but the formula looks quite simple. Quite simple. Okay, so now if I know the values, I know C, I know K, I know F. You agree? Yeah? So I know D initially. I know D initially. I can now step forward in time to get the values of D as I move forward in time. Okay? I really think there's a lot of benefit for you guys to try a differential equation that's time domain. Just make up one. Go to Excel and look for yourself. Try yourself. You're going to see it works out very nicely. And it will give you confidence on this stuff. Okay?
Have we used this to find the values before that could destroy it?
Sorry?
Have we used to find the values?
We're only finding the values in the future. Okay? We're only moving forward in time to find out what the future holds for you. Right? Because that's why it's called prediction. We want to know how this physics problem is going to behave over time. That's the question we're trying to answer. So the next method, using recurrence formula, if I plug in, and I'm answering a question, by the way. If I put theta equals 1/2 here, here, and here, I'll recover the central difference method. And again, you can try it yourself, and you'll find that it does work out. Okay. And then here you have to invert to get di. You'll have to invert this manner to do that. But now I know fi. I know fi currently. I know fi minus 1 previously. I know di minus 1 previously. I know k. I know c. I know di minus 1 previously. I know all this stuff. The time step, you decide that. And then I know the new value of d today, right now, at this point in time. Okay, any questions?
Does FI change for every step?
Fi could change. Because say that the loading that I apply, I'm making a problem up. Don't you think I can have a varying force as a function of time? Right? So I should be able to account for that too. That's where things will influence your results, is a forcing function that's changing as a function of time. In the example that we just did earlier, force is constant.
There's nothing really mathematically special about time as a variable, right? Like,
Your question is there anything mathematically special about time?
well, so we did examples before that was a PD as a function of x and y, right? So what's the advantage of using that method, which is a function of two variables, versus this method?
So what is the advantage of using, so we've never done this before.
Right, but we did a PD that was a function of x and y.
Right, right.
So
Mhm.
we used a different method for that.
Right. So we're using the same method there than we're using today. Okay. We were using finite elements there, and we're using finite elements today. The only difference between what we're doing there and today is that now we have a time that now things are a function of time. That's the only difference.
Right.
So we're not discretizing time using finite elements. That will not work very well. Okay. So finite difference is a much more appropriate technique for this methodology. Okay. And that's how commercial codes such as Abacus and Nastran are coded up. Okay. All right. All right. Any questions? Any questions on this? I know it looks complicated, but it's not. If you plug in theta equals 1, you recover backward difference. If I put theta equals 0, I recover forward difference. And if I plug in theta equals 1/2, I recover central difference. Any questions on that? I can choose a theta that's not any of those. I can choose theta equals 1/4. Okay, that's why it's called a theta method. You can select theta and kind of, you choose the value of theta, in essence. All right, so some notes on this. And that will answer some of the questions in the audience right now. But the forward difference scheme is known to be as an explicit scheme. Okay, backward difference and central differencing are known as implicit schemes. In general, the implicit schemes are computationally more demanding. Okay, but they are more stable. They're more stable compared to explicit schemes. If the errors remain bounded as the time goes by, they do not continuously grow over time. So the value is not getting out of hand. It's oscillating, due to some numerical issue. We call that if that doesn't happen, we call that a stable scheme. It's a stable scheme. If the scheme allows and is prone to unlimited growth of errors over time, you could have a solution that may start oscillating and giving you non-physical results. Okay. The forward scheme, the explicit scheme, forward scheme, they're known to be conditionally stable. I'll explain what that means. Conditionally stable is that the time increment I choose, if I'm smart about it, it can be stable. But if I choose a time step that's maybe too large, you're almost doomed. It's going to go unstable over time. That's what conditionally means. I'm putting a condition on my time step. Okay. And so, sometimes the explicit schemes can be quite expensive because maybe the time step you have to select is too small so that you're conditionally stable over time. When you look at implicit schemes, they're unconditionally stable. I don't care what time step I select, it's more likely that the results as you march forward in time will not grow unbounded. However, if the time step is too large, you could have a larger error. Nobody's disputing that. What we're disputing here is whether the solution will become, it will start oscillating, and it starts growing unbounded with no physical meaning. Okay. And the mathematics behind it is a separate course. It will take too much time to go over this. And for this course, I'm just teaching you the basics. Okay. Although actually it's not basic. What I'm teaching you right now is pretty good. If I was you, I'll be very happy we're covering this here. In all schemes, finite time steps should be selected to be small to capture the unsteady behavior of the solution accurately. You can select large time steps, but that will be at the expense. In implicit schemes, you can select larger time steps, but that's at the expense of maybe a little more error than you will have liked. Okay. However, just to point out too, implicit schemes are more computationally expensive from that in the perspective you have to invert the stiffness matrix or whatever I inverted earlier. You saw I had to invert these things. It's expensive because you have to do that over and over and over, right? All right. So conditional stability. Well, this sounds very mathematical. Yes, it's derived from mathematics, but I have to go through this. So if I took K and C, which we know what K and C is, right? Do we know? What was K? K, 3 by 3, and C is 3 by 3. For this problem, actually, I can calculate the eigenvalues of this formula here. And I'll calculate, how many eigenvalues will I get in this problem? 3 eigenvalues I'll get. If I select the maximum eigenvalue of this, and I plug it in here, depending upon the value of theta that I select, if I select the value of theta, say of 0.2, or let's do 0.2, I get 1 minus twice times 0.2. What is that? I get 0.6 maybe? 1 divided by 0.6, how much is that? 10 over 6. So if my time, my step time is greater than 10 over 6, then I have a situation. I could have a unbounded, non-physical problem. Okay, so there's ways to actually impose these bounds. Notice that for the explicit scheme, theta was 0. Remember that? So that's easy. That's 2 over lambda max. So if lambda is calculated to be 2 here, then the time cannot be greater than 1, the time step. Okay. Otherwise, the solution would become unbounded. For the implicit scheme and central difference scheme, those two, they're unconditionally. Doesn't matter what, they're going to be stable from that perspective. There could be an error, but they'll be stable is what, what's important there in that sentence. Any questions? Any questions? Are you excited about looking into what abacus may do? Let's see what abacus may do very soon, okay? We'll do that. Let's actually do a heat transfer problem. Why not now take a realistic heat transfer problem? And I'm hoping that your homework, which, we'll cover an unsteady heat transfer problem here. So the previous problems that we did with heat transfer, they were steady state. You agree? You applied a temperature. That was a steady state problem. But what happens when things are varying as a function of time? It'll be really cool to see the temperature's changing, right? Not everything. I just calculate a temperature and that's it. Well, in reality, a lot of the issues that occur in real life are not steady state necessarily, but they could be a situation that's not steady state, unsteady. Okay. So in this problem, let's go through the boundary conditions a little bit. I think we need to do that. At x equals -1, at any point in time, well, this domain goes from -1 to 1, first of all. The spatial domain goes from -1 to 1. At x equals -1, at this end, we're saying that temperature is 0. That's what we're saying there. Okay, that's what we're saying there. The second thing we're saying is that is true at any point in time. Now we go here for the x equals 1. So it's telling me that temperature at this end, right here, is 0 at any point in time. That's what that's telling me with that t there. And when you see that t alone, that's just telling you that something's keeping that temperature at 0 degrees. Something is doing that. We don't know what it is, but it's doing that. Then we have another interesting boundary condition here. This boundary condition is saying that at any location in the domain, that the temperature at the very beginning started with a distribution that had this formula, 1 minus x squared. Okay? So in other words, there was a temperature distribution that went from -1 to 1, and that temperature distribution was such that at time equals 0 looked like a parabola. Can you envision like a parabola that starts at 0 temperature, goes to a high value and reaches 0 at the other end? We're saying that time equals 0, that's what's happening. Number two, the thing we're saying is that these two ends, the temperature is fixed at a value of 0 over time. So what do you think is going to happen to this temperature distribution in the middle, which is basically warmer? Sorry? Yeah. I mean, it's t equals 0 here. T equals 0 here is clearly warmer in the middle with a parabolic distribution. If I fix that temperature at 0, you expect the warmth to become close to 0, right? Over time, maybe if you wait 10 days, what do you think the temperature will be across the bar? 0. Absolutely. That's your steady state condition. Okay. All right. So I explained that. I just basically explained that bullet there, and I'll just use 5 linear elements of equal length. That's what we're going to do. Again, I'm going to go a little bit faster now because we need to get going here. But I take form the weak form. I form the weak form. Remind me to remove this t because that's incorrect. The weight function that we're selecting is not a function of time. I form the weak form. I'll use a linear approximation that looks like this. And now ti is at this node and tj is at this node. These are function of time also. This is my approximation over an element. And I'll select a linear approximation. Okay. Now I know that these nodal variables are not a function of x, they're a function of time. The shape functions are spatially dependent. And so then I'll put this in a vector called n. I'll put this in a vector called t. Okay. So I have n times t. I know looking at my definition of the problem, or the weak form, that will have to calculate these derivatives. So I did that derivative with respect to x. That does not depend on x. That depends on x minus 1 over LE. Minus 1 over LE. or 1 over LE, I'm sorry. Then I put these two in a vector called B bold. This I'll put in a D bold, okay? And then I have to take the time derivative as shown in the weak form. And when I do that, these do not depend on time, the shape functions, only these variables. I'll put that in, that's a vector I already called the N bold, if you remember, right there. And then the temperatures are a function of time at each node, so I'll put them in a T bold dot vector.
So why is that PT in second line? Instead of PD, why is that PT?
Oh, I'm sorry. So that's an error in my notes. So can you take a note? The question for the video is why I have a D there. That's a mistake, copy and paste mistake. That should be T bold. T bold. Apologies on that. I use a weak form as shown earlier here. We developed the weak form right here. Then what you get for the weak form is B transpose B dx, N transpose N dx, T dot, and then I have this forcing function, whatever that is. That we know what this is. It's physical problem, so we know this the heat flux applied, maybe. Now we evaluate the integrals for a generic element. For a generic element, this is what I get. L over E, since it's 5 elements, and it goes from -1 to 1, L over LE is 0.4. The element length is 0.4. I can evaluate these things, and I get that. So for a generic element, this is what I get. Now I assemble the system. You have any questions on this? You follow it? Excellent. I'll assemble it. I'm not going to go through the process of assembly because I've done this several times now. But you assemble this. This is called the capacitance in a heat transfer problem. The coefficient to the rate of change of temperature is called capacitance. So this is called in an elastic problem, that's called mass matrix. But in this kind of problem, it's called capacitance. So I have that. That's the matrix right here for basically our K. T1 through T6. Remember there's 6 unknowns, right? Because if there's 5 elements, there's 6 unknowns at each node, right? And then you'll notice that when you assemble it, this goes to 0. You guys can work it out at home, and you will see those go to 0. Okay, so I'm done. That's my global assembly. Now I'm going to impose the boundary conditions. That is my very next step, is to impose those boundary conditions. Well, we already covered, didn't we say that at both ends, I'm keeping the temperature fixed at 0? Yeah? Yes? So, that's why I put 0 there and 0 there. But if the temperature is 0 at all points in time, then what is the rate of change at those two ends? 0. I'm not changing those as a function of time. So, those are 0. So now I'm left with 4 equations, the middle 4 equations. Okay, the middle 4 equations. So it basically imposes the essential boundary conditions of the problem. Okay, and I'm left with 4 equations right there. And now I have a 4x4, and now I have to look at the initial conditions of the problem. I'm not done yet. I imposed the boundary initial conditions. Now I have to look at the initial conditions for the rest of them. We also noticed that the initial condition of the problem at t equals 0, were given by that. Remember that? So, therefore, I can evaluate T2, T3, T4, T5 at time equals 0. We know it's 1 minus x squared. We know where node 2 is, remember? We know where node 2 is. If it's equally spaced, you know where node 2, 3, 4, 5 is. And so the location for node 2 is minus 0.6. For node 3 is minus 0.2. I evaluated that, and I got the values of temperature between minus 1 and 1. I got those values. So these are the values of temperature at t equals 0, and my goal is to find what is the temperature as I move forward in time. That's the question we have here at hand. I used, so before in the previous example I used backward difference. Why we not just use forward difference this time? To try something else, something different. The forward difference method had this formula. And again, this was the generic formula, but instead of D it would be T in our case. Instead of D is T. C is already known, is this one, so you have to invert that to get C. We know K, which is that one right here. Don't forget the 2.5 as a coefficient there. I know F, which is this column, is basically 0. Okay? And then I have the time stepping that I need to select. I have to select the time step for the problem. All right, I'm basically ready to start using it. I know the T, the value of T at the beginning, which was right there, and now I have to just insert that there, select the time step, and then get the new value of T. Okay. All right. Temperature is T.1, so take the value of T at time equals 0, temperature. Take a time step 0.1, and then I get the new value of temperatures right here at time equals 0.1. So at time equals 0.1, that's what I get. At time is equals 0.2, I forward in time again. So take this column here, plug it in here, plug it in there, and then get the temperatures at time equals 0.2. And I get 0.46, 0.47, and 0.46, blah, blah, blah. Right? So 0, 0.46 in the middle, and then 0 again. All right, so now I can continue on and on and on and find, how these temperatures change over time. Any questions on that? What try this in Abacus and see what Abacus gives us. Initially I was very concerned that this may not work out because anytime you try something in Abacus, you know you're going to go into dungeon, right? It's supposed to work if you do things right. Guess what? I had a good day, so it worked out. All right, so let's try this. A discretized domain, here's at the bottom. I have 5 elements, 1, 2, 3, 4, 5. I have 6 nodes, 1, 2, 3, 4, 5, 6. Okay? And I know the coordinates. So I put the coordinates in here. It goes minus 1 to 1. I have the nodes spaced equally. So 1 minus 1, 0.6, 0.2, 0.2, 0.6. So the spacing is about 0.4. You can check it. The element connectivity, I use this element here in Abacus, which allows you to model conduction along a bar. For element 1, the connectivity is 1, 2, 2 is 2, 3, and so forth. Okay. I selected a cross-section, although I don't think that's going to matter for this problem. I don't think it matters what cross-section you select. All right, so before I continue here, I want to point something out. Because there's something exciting about Abacus. You can actually fake Abacus to solve non-heat transfer problems if you understand how Abacus is doing it. What I mean with that, let's say I want to solve electromechanic, or I don't know, just come up with a problem that Abacus doesn't solve, because I think Abacus solves too many things. So anything I say, they probably solve it. So you can actually fake Abacus to use the heat transfer module to solve something else that has a partial differential equation that looks like that. As an example, say I made up this differential equation. Say I made it up for a second. Well, that's what I made up. But if you look at the heat conduction problem, the heat conduction problem has this formula. That's the formula for heat conduction. And so you can quickly identify that rho c is a coefficient for that, that's 1. And k is a coefficient for that, that's 1. Or I can divide this equation by k, and I have rho c over k. I can basically write it in this manner, right? Yeah? So since rho c over k is 1 in our example, I think, I haven't tried this, but if you try any combination of conductivity, density, and specific heat, that gives you a rho c over k of 1, doesn't matter how you select it, you should be able to use Abacus to solve your problem. Are you tracking? I don't know if you follow me. Some of you may not have noticed this, but I can actually use Abacus to solve nothing to do with heat transfer. I can select another problem that has, and maybe rho c and k for my other problem I'm working on have nothing to do with heat transfer, but you can specify what rho c and k are, so it becomes the problem that you're interested in. Do you follow? Okay, so I'm teaching you this because I've done something similar. I've tricked Abacus to solve a non-heat transfer problem. Okay, there's a question right here. Okay, so the question for the video is that what I explained may not be clear. So what I'm saying is, abacus can solve a heat transfer problem, right? The module I'm using is heat transfer, if you see here. Yeah? So what the equation for heat transfer, what is it? This one, right? Yeah? The equation I'm trying to the equation I'm trying to solve is this one for the original problem, right?
Yeah.
So I can relate. Don't you agree that I can just divide this by k and then I have rho c over k like that?
Right.
So don't you agree that I can select rho c and k in any way I want, and as long as I get 1 as a coefficient, I should be able to solve the problem?
Right.
So if it's a heat transfer problem, perhaps, you should put what k is for the material, what rho is for the material, what specific heat is for the material. You should be able to, if I know it's metal or aluminum, I know exactly what these values are. But say I have a different differential equation, partial differential equation that's a function of time. It had nothing to do with heat transfer. I could fake abacus by saying I'm going to use the heat transfer module to solve this problem by selecting rho, c, and k in such a manner that gives me the problem that you're interested in. You follow? Okay, so I did that. I just made everything 1. The initial conditions. Well, I have to specify initial conditions, don't I? So the type is temperature for initial conditions. For nodes 2, 3, 4, and 5, I selected the parabolic distribution. Remember that? Yeah? Then I start the solution, start step, start heat transfer, and then I'm marching. I'm basically starting with a time step of 0.01. I'm going to run this for 2 seconds, and I'm going to not let it. I basically don't want to do anything greater than 0.01 seconds in steps. If you go to Abacus manual, it will explain what each of these are in the keyword section. Okay. The boundary. So the boundary is at node 1, degree of freedom 11, because in a heat transfer problem, degree of freedom 11 is the temperature, degree of freedom. While if you do a coupled simulation, which would be kind of cool to do in this class, then the degrees of freedom for a solid mechanics problem is 1 through 6, right? So they're making 11 like far from this 1 through 6, so I think the data so people don't get confused. For node 1 and 6, the node 11 is fixed at 0. You agree that that looks right? Okay, I'll let you stare at this, couple, like 1 minute before I proceed, in case you have any questions. Okay, this took about, I submitted a run, and I think within a second or 2, it was done. Like it was weird. I thought I made an error. When sometimes you submit a job in Abacus or Nastran, and I'm talking to you too in the back, because you know what I'm talking about. You submit it, you're excited about it, and suddenly it's not in the queue anymore. And you wonder, all that effort I put in, and I had to go back and see what the error is. That's how I felt about this. I submitted it, and it's not in the queue anymore. Did I make an error? I opened it up, and it was solved. So, excellent, very quick. So, let's see, I plotted the temperatures here for all nodes, 1, 3, 2, 3, 4, 5, 6. Because it's symmetric, right? It goes from 0 to 0, temperature 0 in the left-hand side and 0 in the right-hand side. And it's symmetric. The temperature, initial temperature was symmetric. That's why you don't see a lot of colors here. Basically, the red is 1 and 6 lumped in there. I think this next one here, the blue, is 2 and 5, and the green is 3 and 4, right? Because it's symmetric about the center. And you can see here, I started with those temperatures. It looks right. Started with those temperatures, and it drops as a function of time as you expected. It shouldn't cool. I mean, we talked about it. It should cool as time goes by. And it should cool, and it should go down to 0 at the very end. Okay? And I thought this looks correct, actually. Let's look at time equals 0.1. Right? Time equals 0. We should check that. Time equals 0. I plotted it also as a counter plot. You can see it's warmer in the center, cooler at the 2 ends, right? So that looks right. Furthermore, I'm kind of interested to see how this compares to what I did by hand. So at time equals 0.1, although remember here we're using increments of 0.01. When I did it by hand, we just selected 0.1 as a time increment. So it shouldn't compare perfectly. And also I did forward difference, which is another that's another story. So at 0.1, I'm getting temperatures in a center somewhere. Maybe these nodes here, the center 3 and 4 are more in the 0.77 range. Let's see what we got. I can't remember now. I got, yeah, 0.77. Look at that. Not too bad, right? Not too shabby. Let's look at the other ones. I got 0.4 for those. So let's see. If I go here, 0.4. Sorry, what were we looking at? 0.1? 0.1. You know, it's not perfect. I was at 0.44. But you know what? I went 0.1 seconds. That's my time step. In Abacus, I did 0.01, right? So, and I did forward difference. While in Abacus, I was doing implicit, which is more accurate. So that's not too shabby. It's actually pretty impressive. Did I do a 0.2 seconds? Did I do one more? Yeah, I did 0.2 seconds. Let's see what happened there. 0.2 seconds. What is that? About 0.4, not quite. And then for this one, it's a little bit higher. We're not that good there. Clearly not that good there. Okay. In fact, in this particular problem, if I had continued, and I did this on purpose, if I had continued this time step for 0.1, although at the beginning it kind of looked right, the lesson learned that I'm trying to give you here, I use explicit, remember? Explicit integration. In this particular example, if I continue marching the solution, it will have gone unstable. Physically, non-physical. It will have given you results that don't make any sense. Okay? Because explicit time difference method, that explicit scheme requires a conditional. You have to calculate a conditional time step for it to be stable. And I give you the formula. It's 2 over lambda. Lambda is the eigenvalue, max eigenvalue. With that said, I think it would be good. I think to just cover very quick top level, unsteady general ODE problem, and I'll stop with that for today because I think going any further could be not a good day, right, for you. So or for me. So let's just cover just like a summary. Okay, if I have an unsteady ODE problem, any problem I want where C can be different, A can be different, I have a forcing function as a function of time. First step, form the weak form. That's the first step. And here I'm using W as my weight. Okay, as my weight. U is a variable of interest. T is time. A and C are constants. I'm using W as my weight. And so I form the weak form. You guys know how to do that now. You're an expert at doing that. Then, in summary, I take U and I discretize it with separation variables. So I select N, bold, to be my shape function, matrix, vector. U, bold, is the variable of interest, which is a function of time. So I separated the two. I am discretizing over the space spatially with finite elements, and I'm discretizing the time with finite difference. And now I have to take these derivatives, as I saw in my weak form. I have to take these derivatives here, all these three. So therefore, why not get ready for that? I did that here, derivative of u respect to x. That's derivative of n bold respect to s. Let's call that b bold, bu. Derivative of u respect to time, n bold, u dot. N can be whatever. I can make it linear elements, quadratic, cubic. For the homework, maybe we can make it quintic so that you're all week and working on this. No, we will not do that. We will not do that to you. We will plug this in now. We'll plug in this now into the weak form. And when I do that, this is what I come up with. You guys can check it at home. And finally, I get my value for K bold, my value for C bold, and then I get my forcing function here, which is a function. This can be a function of time, by the way. My distributed forces. What if I have a wing and the pressure, the lift is changing over time, right? I should be able to model that too. So you can have Q, F, or the pressure on the structure to vary as a function of time. Okay, so we will then, Sorry. Okay, that's it. This is where we're stopping today, because if I go a little bit further, I think, well, thank you very much for attending, all right? You have a good weekend.